In this video, I want to do an example of finding the null space and the nullity of a matrix. I'm going to start with the matrix that we've seen before. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3 by 3 matrix. Again, to define the nullity and the null space of A, you don't need a square matrix. This one just happens to be square. And what I want to do is I want to compute the null space and the nullity just by hand. And then I'll kind of eventually talk about some shortcuts for finding what these different values are, just so we can talk about shortcuts for the rank. So when I talk about the null space, I want to find all x in R3 so that a times x is equal to 0. In other words, I want to solve this homogeneous system of equations, homogeneous meaning that the right side's all 0. And what I'm going to do, and there's a few different ways that we could do this, but what we could do is we could write this as an augmented matrix, where you augment again, the coefficient matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. You augment that with the constants, in this case 0, 0, 0. Let's make this a little prettier. Put our dotted line. And what we want to do is we want to simplify this as much as possible. Now, the null space of a matrix and the null space of the reduced row echelon form of the matrix are going to be the same, because if you think about what this matrix is, finding the null space really just means tell me about all the solutions to the system. And that's a chapter 1 question, right? Here's a system of equations, find all the solutions, we can do that. And you can do this by doing elementary row operations. And it turns out that when we put this in reduced row echelon form, what's going to happen is you're going to end up with the reduced row echelon form here, 1, 0, negative 1, 0, 1, 2, 0, 0, 0. And then you're still going to have the zeros in the right column, because you're always going to have zeros in the right column. Any multiple of one row plus another is still going to be 0. Any value, any term here times another number is going to be 0, right? There's nothing that you can do to make these not 0. So if you find the reduced row echelon form of the matrix, you can just kind of put that in there. That's why working with the reduced row echelon form of a matrix to begin with is permissible. That's why it's allowed. So what we're going to do now is we want to figure out what are the solutions going to look like there. I think it's important to note that the rank of our matrix, the rank of this matrix is 2, because when we put it in reduced row echelon form, we have 2 pivots. Okay, so the rank is 2. So now let's think about what's the null space. And what we're going to do is we're going to parameterize. Maybe we can let our third variable, say x3, be t. And then the first equation says that x1 minus x3 is equal to 0. So that implies that x1 is t. x1 is x3. So x1 is also t. And then x2 is going to be minus 2t, because the second equation says x2 plus 2x3 is 0. That means that x is going to be negative 2x3, or negative 2t. So what this means is that we have our solution set. And so the null space of A, is going to be the set of all vectors of this form, t, negative 2t, t, where t is allowed to be whatever we want. And we can actually write this in a better way now. This is t times the vector 1, negative 2, 1, where t is allowed to be whatever real number we want. And this turns out to be just the span of the vector 1, negative 2, 1. Okay, because that's what the span of a single vector is. It's the set of all the scaled versions of that vector. And that's exactly what we have. So the null space of A is going to be just the span of this single vector. That means that the nullity, the dimension of the null space, is going to be 1. It's a single dimensional subspace. So the nullity of A is going to be just 1. Okay, so here's the takeaway. For a matrix A, let's again just work with this matrix that we had, 1, 2, 3, 4, 5, 6, 7, 8, 9. We found that the reduced row echelon form of A I'm just going to copy this down for convenience. Was 1, 0, -1, 0, 1, 2, 0, 0, 0. And because we know the reduced row echelon form of A, there were 2 pivots, and therefore the rank was 2. Okay, so the rank of A was 2. Now the nullity of A was 1, and the way that we can tell that the nullity was 1, there's actually 2 ways. One I'll talk about in the next video. It's called the rank nullity theorem. Okay, that's a very powerful or a very important result. But that gives us a relationship between the rank and the nullity. In this case, they add up to 3 because it's a 3 by 3 matrix. So I'll explain why that should add up to 3 in a second, or in the next video rather. But I think a better way to think about the nullity for now is when you think about the span, what this is it's the set of all linear combinations of the single vector. And linear combinations of a single vector just means scaled version. It's all the multiples of this vector. So what you can do when you think about the nullity is it turns out you can think about what's the number of parameters that you have when you parameterize your solution. And we had only one parameter t. And so that's why the nullity was 1, is because we only had one parameter. So the rank you can think of as the number of pivots. The nullity you can think of as the number of parameters when you parameterize the solution AX equals 0. Okay, so that's, I think, a good way to think about the row space, the rank, and the nullity of A.